This video is going to look at atomic spectra and electron orbitals. So we're going to kind of have a little bit of a review of the fun and easy part of chemistry. All right, classical atom. Classical atom, the Bohr atom, it is a nucleus with electrons spinning around it, orbiting it. Physics has discovered a problem with this atom. And modern physics discovers a number of problems that show up, and things that we believe and know make us question. Our problem in this case is we know that charges that are accelerating, speeding up, slowing down, changing direction, emit radiation, energy. So if I have little electrons spinning around the nucleus, they should be emitting energy, giving off energy. But if they were to give off energy, they would slowly shrink in their orbits until they crashed into the nucleus, kind of like satellites. When they lose a certain amount of energy, they crash into the Earth, or if they have unstable orbits as well. So this should be happening, but it's not. So these electrons that orbit, they do so at specific energy levels. Okay, we've noted this, and we've used it in a number of different ways, and it's pretty cool. So if an electron is here, so this little blue guy is an electron. If he's here on this energy level, he's got a specific amount of energy. If he then proceeds to jump up to here, he's got a different specific amount of energy, and that will change depending on the type of atom. So if it's the hydrogen atom, it's going to have one type of energy at that ring. If it is a helium atom, it's going to have a different amount of energy. Okay, but each one is specific to the atom itself and to the ring. To change levels, so if an electron wants to go from here to here, it must absorb energy. If it goes from here to here, it's got to give away energy. Otherwise, it wouldn't drop down. Think about it, if you walk up steps, you got to absorb the energy, take it in. Walking down, la-di-da-di-da, you're giving up energy. All right, so it's like walking on stairs. It's really good to think about this as if you were walking on stairs, because each state or each ring with a different amount of energy, it's very specific. Now, the ground state is like you're at the bottom of the stairs. You're on the ground. After that, each one is above the ground. Each one is excited. Then you can have the first excited, the second excited, and all that. Now, another nice analogy for stairs. Each energy level is a specific amount of energy. So in order to move from one to the other, you would need to absorb or emit, take in or take out, a specific amount of energy. So if an electron is right here at the first ground level, and let's say it takes 1 joule of energy to get to there, and that step right there is half a joule of energy. If I was to say, all right, here, Mr. Electron Bugger, I'm going to give you, let's say, 0.9999 joules of energy. What would you do? You would say, I'm going to stay right here. I'd have to give you exactly 1 joule of energy to make you move up. If I gave you 1.1, you would stay exactly where you are. You need that specific amount. I've always thought about it as, I don't remember where it was I read or saw this, but if you change the height of the stairs, of like one stair, by like a little tiny bit, like almost everyone will fall. Because we're so used to like exact steps that you're going to fall if you have them off even by a little tiny bit. So each one needs to be exact. So if I was to give it 1 joule of energy, it could go here. 1.1, it would stay. 0.9, it would stay. Now if I was to give it 1.5, it could jump up to the third energy level. Okay, so just like stairs. All right, these specific energy amounts are known as quanta. Just a nice fun name. They're like steps on the stairs or rungs on a ladder. All right, so Electrovolts are physics versions of moles. I know, groan, groan, groan. Don't be too sad. They're not bad. A joule is a heck of a lot of energy for a little electron. For you and me, not so much. For a little electron, it's a lot of energy. So we tend to look at things in electrovolts terms. 1 electrovolt is 1.6 times 10 to the negative 19, so a very small amount of joules. And it's just a way to not have big old ugly honking numbers. If you're going from electrovolts to joules, multiply. If you're going from joules to electrovolts, divide by 1.6 times 10 to the negative 19th. If you're dividing, please make sure to use parentheses in your calculator or use the E symbol. All right, otherwise you'll end up with the wrong exponents, and that would make you sad. Or at least make me sad. Hopefully you as well. All right, so I'm telling you each of these energy levels are specific. Now, hydrogen being the simplest of all atoms, we've actually come up with an equation for it. The rest, they're a little bit too complicated, and they change and they're weird, and so we don't have actual equations for them. But hydrogen, we do. If I was an electron in hydrogen on the second energy level, I would have a specific amount of energy. That specific amount of energy is equal to negative 13.6 electrovolts divided by the energy level I'm on squared. Okay, and that's what my E equals. If we were in joules, we'd use this one right here, 2.176 times 10 to the negative 18th. All right, electrovolts versus joules. I'm just going to stick in electrovolts because I have to say 13.6, a lot prettier number than 2.176 times 10 to the negative 18th. So I like the pretty one. So we're going to stick in electrovolts for now. So E is equal to negative 13.6 divided by n squared. So divided by 2 squared. Now if I was to take this and put it in my calculator, it's basically negative 13.6 divided by 4, because 2 squared is 4. And I would get my E is equal to negative 3.4 electrovolts. That's if the electron was on the second energy level. If the electron was on the first energy level, then it would have E equals negative 13.6 divided by 1 squared, because your n is 1. And E would equal negative 13.6. Okay, so as you see, as you get farther up, your n's go up, your energy goes down, because it needs less energy because it's farther away from the nucleus, so it needs less energy to overcome that attraction. Now this third equation down here, and if you wanted to do it in joules, you just have to use this constant rather than 13.6, is what happens when you change energy levels. So for example, if I was to go from 2 to 1, I would say, all right, how much energy was absorbed or emitted, taken in or taken out? That would be negative 13.6 times 1 over the final n, which in this case was 1, minus 1 over the initial n squared, which was 2. So negative 13.6 times 1 minus a quarter. So that would be negative 13.6 times 3/4. All right, so 13.6 negative times 3/4 is 10.2. So my change in energy is negative 10.2. Okay, so it's negative because it's dropping down, so the change in energy is negative, which means it is giving off energy and therefore, being emitted. So it's losing energy, so your change in energy will be negative. Now, if you don't like this equation, that is perfectly fine, because if I was to take this that I did up here and say, okay, this is what I ended with, this is what I started with, negative 13.6 final minus initial minus negative 3.4, that is also equal to negative 10.2. Final minus initial. So if you don't like this thing here, that third equation is just, making 3 steps into one. If you solve them separately, find each E and then subtract them. You can do whichever makes you happy. Now, the N's you've been seeing are the energy levels, and they go 1, 2, 3, 4, 5, 6. All right, so energy, not created, not destroyed, always there. That energy, we said, is given off in form of a photon. Okay, so one way we know how much energy is given off, and the way we figure out the specific energy levels for each one, is we figured out the frequency of the wave or the photon emitted, and therefore we know the change in energy. So in this case, 10.2 electrovolts of energy was emitted. Okay. Now, H is our Planck's constant, which we've already seen, and that has the units of joules times seconds. So we need to get that electrovolt into joules. So we multiply by 1.6 times 10 to the negative 19. And we can get our amount of energy in joules. All right, so we get 1.632 times 10 to the negative 18 joules of energy. So what would be the frequency of that photon? That's how much energy it gave up. What would be the frequency? Well, E equals HF. So that equals 6.63 times 10 to the negative 34th times F. And the E is that 1.632 times 10 to the negative 18. So all you got to do is divide it by Planck's constant. I'm just going to write it as an H. You can write it as the 6.63. And I get a frequency of 2.46 times 10 to the 15 hertz. Okay, so you can also work backwards. If I was to measure the frequency of a wave emitted, I could tell you the drop of the electron. Okay, so the change in energy in the atom is equal to the energy of the photon, which is this point right here. If your change in energy is greater than 0, so positive, that means it absorbed energy. The energy level went up. And that's along the lines of, if I shoot light at it, it can take in that energy. And if your change of energy is less than 0, then it was emitted. Okay, so if energy is emitted, and we've done this, okay, we found our frequency. We can also find our wavelength. Okay, this right here, this step, is basically saying frequency is equal to V over lambda, which we know V equals lambda F, just rearranging that equation, and our velocity, because it is electromagnetic wave, is equal to C. Okay, so if I was to find this wavelength and plug it in, I could find that my wavelength is equal to 1.21875, so 1.22 times 10 to the negative 7th nanometers. And you'll see these a lot in nanos. That's just times 10 to the negative 9th. So I took my answer and I multiplied it by, oh, sorry, that's meters. So to go from meters into nanometers, excuse me, that was negative 7th there's meters. To go into nanometers, I would multiply by 10 to the 9th. So that would actually be 121.875 nanometers. So if I was to look up at this scale and try and figure out, where it is, it would actually be pretty far down here. So it may not be in the visible light spectrum, but you kind of get the idea. So if the electron emits energy and it gives off a light that has a wavelength of 656, you can work backwards to find out how much energy was emitted. And these emission spectrums are used quite a bit in figuring out like what type of atom it is. And I'm sure you guys either in middle school or in high school has done the flame test, where you take a chemical and you basically set it on fire and it becomes pretty colors. Well, those pretty colors are dependent on the type of material. Also, another way to think about it is neon lights. Neon lights change color, or you have different colors depending on the type of atoms in there, because that's the emission spectrum. That's the amount that the electrons will drop and give off energy. Okay, and that would change based on the electromagnetic spectrum. I love this graph. This is actually from Wikipedia. It's beautiful. They did a wonderful job of it. This is the visible light spectrum in here. Okay, these are your frequencies. Your wavelengths are up here. So a wavelength of, let's say, a radio is about the size of a building, while the wavelength that we see is something between a needlepoint and a protozoan. Okay, so depending on the wavelength we get would depend on where it is. So it was times 10 to the negative 7th for the hydrogen. So that would be somewhere about halfway in between here. So it would be somewhere between visible and ultraviolet light that electron would give off. Absorption spectrum. Actually, I didn't know this until I started teaching last year. I thought this was pretty cool. We can figure out, and this is how we figured out what the sun is made of. We take the absorption spectrum. So the sun absorbs these specific photons at these specific lights. And we can say, okay, well, if it's absorbing, let's say, this isn't exact, but this one, and this one, it must have hydrogen. If it is absorbing this one, this one, this one, this one, and this one, it must have helium. So we figure out what gases surround the sun by seeing which lights are absorbed. Pretty cool, huh? Now, hydrogen, we have that specific equation for. All the rest, they're a bit too complicated to have such a nice, easy equation. So you're going to get charts like this. Okay? Charts like this are lovely. They're wonderful. They tell you basically the energy at each one. So if you want to find out if something is dropping from, let's say, N7 to N3, so from the 7th to the 3rd energy level, you'll say that's 2.48. That's 4.95. And the difference is the energy absorbed or emitted to do that, to transfer between those two. So 2.48 and 4.95, 2.47. And it can be positive or negative depending on if you're going up or down, electrovolts. Do keep in mind the units. Okay, so those are beautiful, and you'll love them, and they're easier than the hydrogen equation, which is not bad in itself. Energy is a scalar, so when you're going in and solving for the frequency, you're not going to have a negative frequency. Okay, so you can kind of just say, all right, what's the difference? And that's my energy level. What happens if I give it more than, in this case, 10.38 electrovolts of energy? Everything needs a specific step, except the one last key, and that's ionization. If I give it more than 10.38, or if it's here at the fifth energy level and I give it more than 3.71. Basically, I've given it enough to ionize it. So if you think about pushing someone across the room, well, if you push far enough and hard enough and long enough, you're going to push them out the door. Same idea with the electron. You push it hard enough and long enough, it's going to leave the atom altogether. And that's known as ionization. Okay, so if you give it just enough energy to leave, it's merely going to leave the electron. Anything extra, so let's say it was here at energy level 1. And instead of giving it 10.38, I gave it 11.38 electrovolts of energy. It's going to have 1 electrovolt of kinetic energy left over. So all that extra energy left over is kinetic, which means it's going to just keep flying down. So you pushed it, and you gave it extra, so it's just going to fly away. All right, real quick example. An atom, only electron is on the 4th energy level. How many different photons can be emitted? All right, so it's going to step down. It's going to go from 4, there's a 3, there's a 2, there's a 1. Now, it doesn't have to step down in one step, but it can. So if it starts at 4, it can go from 4 to 1. It could go from 4 to 2. Now, if it's on 2, it's going to go from 2 to 1. It can go from 4 to 3. Now, if it's on 3, it can go from 3 to 2 and 2 to 1. We've already had that arrow, though. Or it can go from 3 to 1. Okay, so it can drop down in any number of ways. And, you know, every electron will be different. If it's giving off energy, it's going to give off a variety, and that variety is going to be there. So in this case, I have many arrows. I have 1, 2, 3, 4, 5, 6 different steps. So it's going to give off 6 different emission spectrums, so 6 different frequencies. This is what it's going to emit to go from 4 to 1. Now, what's the frequency of the photon that would be emitted if the electron returned in a single state? So it had 15.8. Ground state is 15.8. It was at 2.34. So 15.8 minus 2.35 gives me how many electrovolts of energy? (13.45 electrovolts of energy. If I take that 13.45 and multiply it by 1.6 times 10 to the negative 19th, I get the amount of joules. To get the frequency, I'd say, okay, this is how much energy was emitted. That's how much energy the photon got. So you have a photon, E equals HF, of 2.152 times 10 to the negative 18th equals HF. Divide by H, which is Planck's constant, of 6.63 times 10 to the negative 34th. And I get a frequency equal to 3.246 times 10 to the 15th. All right. That's it for the lesson. Good luck on your homework.